Lesson 3.3, correlation. A correlation, indicated by the variable r, is going to measure the strength and direction of a linear relationship between two quantitative variables. Some important properties of the correlation are, it's always going to be between the values of -1 and +1 inclusive. If the relationship is negative, then r will be negative. If it's positive, then r will be positive. If it were to equal +1 or -1 exactly, that means that all of the points are exactly on a line, which is something that happens very rarely with real data. And lastly, if there's very little scatter from the linear form, meaning that all the points are very close to a line of best fit, then r is going to be close to +1 if it's positive association, or -1 if it's a negative association. The more scatter, the more spread out around that line of best fit, the lower r gets approaching 0. To give you a better idea of what to expect from correlation values, here's 6 scatter plots with their corresponding r values. So in this first one, we have really spread out points. It's impossible to tell, is this going uphill, is this going downhill? Really, it's a flat association. It's all spread out, and the correlation is equal to 0. In the second one, we can see somewhat of a trend here. This is going downhill left to right, but it's still really spread out. So our correlation value is still somewhat close to 0. It's negative because it's going downhill, and the fact that it's 0.3 means that it's spread out from that line of best fit. Now we have an uphill one, okay, a little tighter with regards to the spread than that last one. Positive this time because it's going uphill, and a moderate association of 0.5. Negative again because it's downhill. All right, and we can see as those points move closer to the line of the best fit, this is going to, I'm going to use the word increase, although it's really getting smaller, but it's increasing towards a -1. -1 is when they would all fall exactly in a line going downhill. Okay, so here we see one with much tighter spread still. That's 0.9. It's approaching 0.1, which would be a perfect correlation in a straight line. And then lastly, -0.99. We can see those are very close to the line of best fit. So here's the scatter plot that we were introduced to in the last lesson, showing the relationship between 40-yard dash times and long jump distances for a class of 12 students. It tells us that the correlation is -0.838, and it asks us to interpret this value. So the fact that it's negative tells us that it's going downhill. All right, so we would know it was a downhill association even if we didn't see the scatter plot. And the other thing it tells us, since this value is somewhat close to -1, it's telling us that those points are not too spread out. So if we were to write that into a sentence, the correlation of -0.838 indicates that the relationship between these two variables for these students is strong and negative. Just a note that if we have a correlation that's close to 1 or -1, it doesn't necessarily mean that we're dealing with a linear association. For example, this graph that we saw in the last section has a strong correlation of 0.93. Okay, it's telling us it's positive. It's telling us it's close to a line of best fit. However, it doesn't tell us that it's linear. Okay, this is not linear, and instead we have a curved association. Okay, correlation alone doesn't provide any information about what form this scatter plot is. And in order to see that, we really need to look at the graph. And while the R value is a good way to measure strength and direction, it has limitations, mainly that we don't want to assume that just because two variables are strongly correlated, that there's some kind of cause and effect situation going on. So in a lot of cases, we might see that in a scatter plot, two variables that have a really strong correlation, but it's not necessarily that one variable is causing the change to the other. And to demonstrate that, we have this graph here. Along the x-axis, the explanatory variable is revenue from skiing, and the y-axis, the response variable, is the number of deaths per year from people who get tangled in their bed sheets. And this is real data. Apparently this really happens. And we can see that this is a very strong correlation. These points are really close to that line of best fit. It's not very spread out at all. The R value here is actually 0.97. It's almost perfect. 1.0 would mean that they lie perfectly in a line. Now, obviously, as more people go skiing, or as ski resorts earn more revenue, more people are dying from being tangled in their bed sheets. So does that mean that as more people go skiing, it's causing more people to die by being tangled in their bed sheets? Maybe they're just so tired after skiing that they go back to their hotel and accidentally smother themselves in a bed sheet. And that's obviously not the case. This is not causing the other. Okay, there's something else at play here. We have what's called a lurking variable, something that's affecting both of these and causing them both to increase with one another. And in this case, it's just population growth. All right, as the U.S. grows in population, you have more people going skiing, which is increasing that revenue. And with more people, there'll be more of these weird situations where people die from being tangled in their bed sheet. So just keep that in mind, that even when we see something that's really strongly correlated, it's not necessarily the case that one of these variables is causing the other.